Gonna buckle up. Exactly, vector basics. So first of all, we need to start with the definitions of a vector and a scalar. So those are the two kind of definitions. Maybe this is going to remind you of some first year physics. What is the definition of a scalar? A scalar is anything that has magnitude. And then if I ask you, well, what's the definition of a vector, chat? You guys say... There's going to be a delay always with these kind of things. Magnitude and direction. Excellent. Good job, team. I'm proud of you. Magnitude and direction. Exactly. So, a thing that we tend to associate direction with is usually an angle. So, a vector is a thing that has magnitude, i.e. it's a number. Magnitude is how big is the number. And it could be a unit there. It could be meters per second. But it could also be certainly in a direction. So usually we have the positive y-axis, negative y-axis, positive x-axis, negative x-axis. I'm just looking at the camera to make sure that you guys see this correctly. So this is the negative x-axis and this is the positive x-axis. So assuming we humans tend to like the x-axis first, we tend to go left and right instead of up and down in the air. That's a bit awkward for us as humans. I know it's a bit weird. So we tend to associate the x direction as a positive, this way. And what we tend to do is, let's say I'm going at 2 meters per second in this direction. But I could also have an angle with me. Instead, I could have a 25-degree angle in the x direction. So we'll be in this x direction with an angle of 25 degrees and I'm climbing uphill. And so that angle, that is that direction that we associate with this. We are quoting airplane. Oh, Roger, Roger, Victor, Vector. Yes, that part I understood. "24 degrees crosswinds." Okay, so let's do some simple introduction to vectors. So let's say we have a car. We're driving a car and we're driving it in this direction here. Arbitrary direction. And the direction that it is traveling in is northeast. Yeah, that's east. Just had to double check there. And it's traveling at 20 meters per second at an angle northeast of 25 degrees. Okay? We can break down this component. This is really hard because let's say it's driving in this direction or it has a force in this direction and then another force clashes in this direction or another force begins acting in this direction and all these forces acting on top of it, add and subtract them easily. Weird. Things get weird. But in 2 dimensions, we can deal with this really, really well by just extracting its x component and its y component. So what do I mean by that? Well, if you remember graphs, we have this y-axis here, and we have this x-axis here. That is us plotting in 2 dimensions. We also have 2 other dimensions associated with it. It could be also in the negative direction. So this is the negative x, and this is the negative y. So, generally speaking, yes, we're 3-dimensional beings, and we deal with 3 dimensions. And if I wanted to, I could add a 3rd dimension there. For health and safety, for making this problem a little bit easier, let's ignore that for now and just deal with 2 dimensions for now, okay? And we tend to like 2 dimensions. Like if I were giving you directions to the shop down the street, I would say, oh, turn right, go about 4 blocks left, and go straight ahead. I wouldn't say you also need to climb a 10-degree hill northeast something, something to bear in mind. Thank you for letting me know, Spooky. I'll be aware of that. I'll try not to talk when I'm on the board. I need to turn my head around when I speak anyway, so it's a good practice for sure. Now, after all that rant, what we can do with a vector, which is really, really interesting, is that we don't care about the position of a vector. Yes, I can give the coordinate that originates at a 0, 0 position, as in the x point 0 and the y point 0. But what we can do is any vector that is given, we can always just grab it lift it, and pick it up anywhere we want it. So I've picked up this vector and I've put it on this board to make things a little bit easier for me. It's traveling at 20 meters per second in this direction at an angle of 25 degrees from the x-axis, okay? Now, if we wanted to do maths with this, things get hard. It is very complicated. The difficulty in this is that, well, if we want to add some vectors, like let's say it starts traveling at 27 meters in the x direction afterwards, you're like, oh Jesus, how do we start? How do we add those two things together? Because that angle fucks things up, basically. So what we need to do here is we need to extract what the x component is and the y component. Basically, if you're pushing something like this in this direction, okay, what you're really doing is you're pushing it this way and you're pushing it this way. You're doing a combination of those two things. And the sum, or not sum, a weird Pythagoras thing that we have to do to it, is what the actual force of us pushing a block at an angle is. So in this direction and this direction, we're going to do a bit of maths to solve what the net force is at that angle. In this case, it's the speed. What is the components of the speed in the x direction and y direction? So what we need to do is classical old Pythagoras' theorem, or sine, coses, and tans. Actually, Pythagoras' theorem is the opposite way. Bear with me. We're going to do classic sine, cos, and tan. So if you remember your triangle rule, it's a right angle triangle. There's our angle here. If this is our hypotenuse for this angle theta, opposite the angle is opposite. And beside the angle adjacent to it is adjacent. So if you remember your sine, coses, and tans, sine of theta is opposite over hypotenuse. Cos of theta is adjacent over hypotenuse, and tan of theta is opposite over adjacent. Hi, Tetsu!
That still only counts as one.
Sorry, I have to have the coffee occasionally. Okay, so we have sine, cos, and tan. Well, we actually have the value of the hypotenuse. We also have sine of theta, cos of theta, and tan of theta, because it's just 25 is the angle, which means that we have only one unknown in each set of these equations. That's freaking brilliant, except for this last one here. So we can use these to calculate what our values of the x and y direction would be. So let's do that. So this is opposite. This is adjacent. Let's do opposite first. Let's calculate, oh no, we'll actually do adjacent first, just because we'll calculate the x first. So, that is cos of theta is equal to adjacent over hypotenuse, cos of 25 is equal to adjacent. If hypotenuse is being divided over here, we bring it across, we must multiply it. So it's over here. The hypotenuse is 20 meters per second, cos of 25, and that is our x direction. If you want to grab your calculators, I think I have my calculators. 20 cos 30. 25, sorry. Be careful about your, make sure your calculators are, in the correct dimensions. 18.13 meters per second. Now, I don't know if I did the maths right, but I know that, degrees, not rate, thank you, Bog. Make sure your calculator's not in radians. The question is, does this answer make sense to me? And I'm going to say yes. Why does 18 look okay? Why is 18 meters per second okay of an answer to get based on what we can see now? Mental maths, a bit of mental maths here. Well, not even mental maths. Common sense maths. It's not actually common sense, it's just maths. It is less than 20, exactly. If you remember your trigonometry, the hypotenuse is always the biggest guy. So your x value and your y value, each one of them is going to be less than the hypotenuse value. They cannot be bigger, otherwise it can't be the hypotenuse. So the fact that we got less than 20 is a good sign. We did something right-ish, arithmetically. Arithmetically. Why is that word weird to me now? I'm not going to say it again. Hi Nexus, welcome in. Repeat the step again, but now we want to find what the y direction is. So this is the x direction. This time it's 20 sine 25. So remember, sine theta is opposite over hypotenuse. This is the y direction. We're looking for the arrow this way and the arrow this way. So in your calculators, shove that in there. 20 times sine 25. And I got 8.45.
That still only counts as one.
Okay, that looks correct. Excellent. I'm glad we're confirming my mental maths. Oh, not mental maths. I'm mental. Ooh, my face is itchy. 2 seconds. Very itchy face there. So what we've done is this thing that was expressed at 20 meters per second and at an angle from the x direction at 25 degrees, we know that it's traveling in the y direction at 8.45 meters per second, and in the x direction, it's traveling at 18.13 meters per second. Now this is very useful to us because if we begin to brake, or in this x direction there's a oppositional velocity force of 2 meters per second, we can actually do maths with this. This is useful. We've expressed it. We can express it in a few ways. One of the ways that we can express it is as probably should put in the unit there, meters per second. But what we've done is we've expressed it in a partial x vector direction and y vector direction. So we're saying that it's traveling in this direction in the x plus in this direction in the y. Now, or this magnitude, sorry. Now, I wanted to say something. Something that we do with vectors is we don't tend to use x's, y's. And if it was a third dimension, we'd use z, right? We're three-dimensional beings. We have up, down, right, left, forward, backwards, right? We have 3 dimensions. And we can use z there. But usually in physics, we don't tend to use x, y, z to express position coordinates. We use other letters. Does anyone know what letters I'm talking about? Hi, Trooper Truth, welcome in. Let me know if the music is too loud. I call them numbers. We use different letters. Does anyone know what letters we tend to use in vectors? Does anyone remember? It's not X, Y, and Z we tend to say. We do use them. We do use X, Y, and Z, but then we kind of replace them. VUs for velocity, initial, and oh, we do use VUs sometimes, yes. Some stupid Greek letters. No. There we go. Egdad, welcome in. Thanks a million for the follow. Your first comment is being the correct comment. IJK. JK. No, I'm not JKing actually. IJK. Those tend to be the letters that we tend to use in physics and notations because X, Y, and Z is used for position coordinates usually, but also there are the unknowns. You know the joke, oh, I'm trying to solve for my X? We tend to use X, Y, and Z for those kind of things. So instead we tend to use IJK in in vector analysis or vector position definitions. So really what we would say is 18.13i plus 8.45j. There we go. Still got it. Nice. You're joking. So that is the idea behind it. Now we can work backwards. Another thing that we can do with vector analysis. Sorry, I hope my 3D printer isn't too loud. Do you guys hear it? There's a big ass project printing at the back. It's like my biggest project yet. Well, that's not true. I've printed other, but this is my biggest project that I did independently. Well, with chat. Of course, chat helped me. Forget chat. That still only counts as one. Printing a big ass. You would want that, wouldn't you, Spooky? Now, let's say have our axis again. Let's say I'm traveling in this direction at 2.6 meters per second and in this direction at 4.9 meters per second. Okay, shit. And I asked you, give me the resultant vector, that hypotenuse value, and the angle, the direction. This is weird because we don't have a triangle, chat. Look at this. That's not a triangle. see you, Tetsu. Hi, Mr. Tofi. Welcome in. Hello, Misho. Good day. Hello, thanks for welcoming. I'm confused that the previous sum was greater than it. That's okay. It's okay if the sum of those two vectors is higher than the hypotenuse. That's fine. But each individual vector has to be less than the hypotenuse. We're doing it via trig if we can. Vectors can be put anywhere. Exactly, Blitzcrank. Exactly. Can I go to the bathroom? No, Bog. I'm not giving you a toilet pass. Put your butt right down on your chair and keep studying. So, a thing that we can do with vectors is we can kidnap them. We can do whatever we want. Well, not really. But what we can do with vectors is we can kidnap them. We can grab them and place them anywhere we want on the board, but as long as they're the same size and in the same direction. So what we're going to do is we're going to kidnap this 4.9 meters per second and we're going to move it here. Okay? 4.9 meters per second. Hi Grim, welcome in. Sounds illegal. No, this is the only legal kidnapping you can do. So we've kidnapped it. Now we can get a rectangle, a triangle out of it. So, draw it like this. There we go. This is the resultant vector R that we're looking for. And now we have a normal angle, theta. We have the right angle, so we can manipulate things with sine, coses, and tans. Van to the vector analysis. Hi, Nat. Welcome in. Okay, so let's do a little bit of mathematics here. Do we remember Pythagoras' theorem? I saw someone write the equation earlier. Good old Pythagoras, who believed it wasn't asparagus, it was fava beans, wasn't it? Yes, he worshipped them. And Pythagoras was a genius, yes, did loads of amazing mathematics. But just FYI, he did believe that every time you farted or burped, some percentage of your life was being lost. So the more you fart and the more you burp, the more you, the closer to death you are. So maybe some of us are more screwed than others. But yes, you're absolutely right. A squared is equal to B squared plus C squared. That is Pythagoras' theorem. Doesn't matter which one is the B and the C as long as they're appropriate. The idea behind it is this is B squared, this is C squared. What I do when I teach this is the lettering I use. R squared, A squared plus B squared. This guy is A or X. We'll say, just for, because we know vectors, we'll say this is X. We'll say this is Y. And this guy, R, is the resultant vector. Capital R, resultant. Hi, Avatar. He worshipped, I thought it was asparagus. I think it was fava beans, specifically. I think it was fava beans. Hi, Gossie. He did have a cult, that's true. Was it a sex cult or an anti-sex cult? Most confused. Usually when physicists join cults, they're into either super anti-sex or super pro-sex. I always forget which one. Okay, so the idea behind it is then, if we wanted to find what our resultant vector R is, we would need to square root, because it's a squared there, to get rid of it, we square root both sides. The values of X, 2.6, and Y, 4.9. So let's do that in the calculator. All under square root, 2.6 to be squared plus 4.9 to be squared. And I know it seems redundant, but you will get a different answer. It is important that you do square them and put them under a square root. So 2.6 to be squared. Oh no, I forgot to square. I just said, what did I just say, Tofu? Listen to your own advice, will you? .9 to be squared. We get an answer of almost 5.5 seconds. And that roughly looks correct. That looks good for us. Aren't lab rats a cult? That is true. That is true. We are a cult. Welcome in, Science Fish. Okay, I'm going to ask you, Bog, why does this answer look correct to you, chat? Why does this answer not seem bullshit to us? A 3D printer is doing crazy stuff over there. Because 5. Exactly, excellent, because it's longer. 5.5 is bigger than both 2.6 and 4.9. I know it's a small thing, but I'm trying to kind of, I always do this with my own students. If you're like me and you're super lazy about double checking your mathematics, I never double check my maths, I'm really, really lazy. A good thing that I just do is just check rough estimates. Like do a quick magnitude maths in your head, number 1, or 2, little concepts and ideas that you can check really, really quickly. One of the classical things to do as well is, if you're doing a proper physics problem, is just quickly look at the units. Like if you had mass multiplied by distance divided by time. Just quickly check out the units and make sure that they work out, because if they do, then chances are you did something right. Worst case scenario, you did an arithmetic mistake. And usually, unless, like, I don't know what other lecturers and teachers are like in the universe, arithmetic mistakes do not get punished severely at all. If even. Well, no, if you don't get the right answer, you do have to be docked. But it's very, very tiny usually. Now, good point about the angle. Which one should we use, chat? What information do we have? Do we use sine of theta, cos of theta, or tan of theta to solve this? What do you think? It is FTL music, it is Grim. Yeah, you're right. Tan. Why did you choose tan, Bog? Why not sine or why not cos? Same with Gunder. Why not? But I have hypotenuse as well though now. It's true. Zero does have a point. You're absolutely right, Bog. You're absolutely right, Gunder. The good idea here is to use tan. You can use any one of them because we have all three. But it's best to use tan here just because we are given the values of tan. So let's say we did make an arithmetic mistake and we were being a bit of a tofu and we made a mistake. At least this way, we're using their numbers and we have a redemption arc of not making a mistake second time round. Is opposite over adjacent. Opposite is 4.9. Adjacent is 2.6. And another thing we're going to do is we need to put the tan across. That's arctan. Oh, sorry. Theta is equal to arctan 4.9 divided by 2.6. Actually, I call it arctan all my life, but I was teaching my students this year and they told me they'd never heard of the term arctan or arcsine. Did anyone else in chat ever hear that before? Or am I making up words? Am I crazy? I could be crazy. But my students pointed out to me that they never heard that term before. I know the arc prefix. Did you use it with the tan? Yeah, I just call it inverse tan. Okay. Yes, that's what I think it is, Gossie. So that's the word I was using the whole time, but the students were unfamiliar with that term. Yeah, okay. Okay, I don't have arc on my calculator. My calculator just has tan to the -1, tan to the -2. Yeah, I had arc as well. Yeah, a lot of my students have never heard of that before. I was wondering if it's an old thing. Maybe people don't say arc anymore. Chat, we're getting old. Maybe we're getting old. Anyways, here we go. We got the angle to be 62 degrees, so our resultant answer is our vector. What's our vector, Victor? It is 5.5 meters per second at 62 degrees this way. So from the x direction, 62. Excuse me, I'm burping. No, it's the children who are wrong. Exactly, Jimmy. Hi, Tris, welcome in. All right. I'm happy to pause here as this is the first chapter of the lesson for, not today, sorry, just for now. We're still going, we still haven't done, but this is crash course introduction to what a vector is and how to do simple vector maths, okay? So now we learned that we can express vectors as resultants, and we can express a resultant vector in its x, y, and z coordinates. And what's really interesting is that even though we're working with 2 dimensions, we can always work in 3 dimensions. That's usually kind of the idea behind them. Have you ever seen an angle being E of S or S of E? South as in, yes. It's a bit weird because you need to know, are you working with the unit circle? Yeah, it's hard to know those angles. Those are weird always. Okay, so that is part 1 of physics done, or intro to vectors done. Because now what we're going to do is we're going to work with some rules in vector analysis, specifically multiplication. So I think the biggest thing about vector analysis is that it's a pure mathematical thing, but it's applied in matrices, computers, physics, engineering. We use them across the board, right? But what we need to kind of remember about this, or keep our minds in, is that whatever we're expressing as a vector, probably, especially in physics, is expressed as something, a behavior in physics. So for example, this could be velocity. We're talking about a object moving in three-dimensional space at a certain velocity. And what's so cool about it, which is like not today's lesson, but another time, is vector differentiation. Because then what we can do is we can do calculus on the vectors, which means that when we have a position of a particle, we can know its velocity. Hold your horses. We can also know its acceleration, or vice versa. If we know the acceleration at a certain time and position of a particle, we can also know what its velocity is, and we can know its position. By using integration and differentiation, we can work backwards and forwards about a thing that is moving in three-dimensional space. It could be a force, it could be a projectile, it could be... I'm trying to think of other examples. Basically, anything that can be expressed as a vector, we can do some crazy and lovely, amazing maths. That is brilliant combination of emotes, Wombat Hole. Jesus Christ. Archery, there we go. So, I'll just sit down for a minute. Rest. And then we will move on to the first vector analysis mathematical aspects, and that will be dot product. The first part we're going to do is the dot product. Oh, my feet are killing me. I don't know why I get really tired on stream, because I lecture on my feet all day. The scalar product, that's right. So the dot product, we're going to get a scalar value out of it, and then the cross product, spoilers, is going to give us a vector output. Oh fuck, eigenvectors. Eigenvectors. Thank you.
And they call it a mine.
Hey!
A
Thank
mine.
you so much, Apple Wolf, for giving a community gift sub. Really, really appreciate that. 2TV, thank you so much for your prime. Oh, Pega got it. I'm glad Pega got it. Lovely, lovely member of the community. Thank you so much for the gift subs, Labrats. Appreciate it. I appreciate you holding off until we got to the break. That's a dream covert data, I think. It only works if my lab rats are paying attention to me. I hope my lab rats are paying attention. I'm keeping an eye on you. We won't have extra rations if you guys aren't being good. That goldfish by Fizzy, so good.
It is possible to commit no mistakes and still lose. That is not a weakness.
That is life.
That is life.
We always pay attention. Lies. Lies. Oh, just... Did oil the access today? Who? What? Oh, a squirrel. That still only counts as one. Let's clean the board now. I sat down for a whole 2 minutes. No, I'm going to sit down for 30 more seconds. I'm going to run 30 seconds of ads to get rid of the payroll. P-roll? What word am I looking for? Yeah, anyways, 30 seconds of ads. Pre-roll, that's the word. Beta roll. Oh, jeez. Look, English isn't my strong suit. Clearly, being a physicist has changed that. Right. Let's clean up the board, and we're going to start a new topic. P-roll anyone heroes, sending them to the mines. Where do you guys pee in the mines then? Right. Give it a few minutes to dry. Don't you review our oh wait, that was Bog. Swiss roll. Again, Apple, thank you so much for gifting a gift sub to the community. I really appreciate it. 2TV, thank you so much for your prime. We always appreciate all and any support on this channel. But as always, especially with Christmas time, take care of yourselves and your family and your friends. Make sure Twitch streamers are the last people on your list. Unless they have bunnos. Unless they have pet bunnies that need to be fed because, you know, it's Christmas time. And that floof needs to get floofier, you know? You know? Alright.
71 years is far too short a time to live
Bog.
among such excellent and admirable hobbits.
Bog!
I don't know half of you half as well as I should
For the
like,
Bono!
and I like less than half of you half as well as you deserve.
Choo choo! Motherfucking choo choo!
Thank you so much for kicking off that hype train, Bog. Thank you so much for 10 gift cards to the community. Let's go. And of course, Bunzo is... I was going to say she's grateful, but she's not. She's a little shit. She's not going to be grateful at all for that. Yeah. Hi, Drew. No. So this is the deal
on the menu, boys.
And it's not critical mass yet. We'll make it go critical mass soon. We're just 3D printing its case at the moment now. One of the two cases. Scam Train Sacrifice. Spooky, thank you so much for the 111. Again, thank you so much, Bog, for those 10 gifted subs. You're very, very kind. Do you guys get discounts? Is there Christmas discounts on? Because I tried to activate discounts, gift sub discounts for stream, and I haven't been able to do so. And Chubby on top. All right, while we have a hype train active, and I am very, very grateful for that, lads, thank you, we will continue with the lesson and we'll start with the dot product. What's very fascinating to me is that when I was teaching maths to some people, I used to reference English textbook. Actually, sorry, not teaching, when I was learning maths by myself at home. I learned multiplication as a dot. So 2 dot 3 is equal to 6, right? And then when I went to school, in primary school, and I started learning in Ireland how maths, they were using the X sign, right? And when I used the dot, I was given out to. Obviously, my teacher said that's wrong.
A mine.
In reality, that's not the case, of course. The X and the dot still mean the same thing when we're talking about singular values, single multiplication kind of aspects. But it's actually an important difference when we talk about vectors. The dot product and the cross product actually mean two different things. Sman, thank you so much for the 12 months, one whole freaking year. Thank you. That still only counts as one. Yeah, so we actually use the star sign as well, Grim. That star asterisk. We use that in Russia as well, or the Russian textbooks I've read. So I read a thermodynamics book, and it uses that sign as well. Yeah, round brackets. So I'm curious, when you were in school, in primary school, like when you were a baby in school, I'm gonna do a poll. What did you guys use?
Only counts as one.
First multiplication symbol. Multiplication symbol. Was it a dot? Was it an X? Was it a star? Or was it other? Was it a 1 and a 2? Was it 1 and 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 2? Was it Just a curious poll, specifically not in secondary school, not like when you're in high school, the first time you did it when you were like 8 years old, or however old you are when you first do multiplication. I don't remember. You guys remember what was the first symbol you were taught? So I have a poll there, just out of curiosity to see what you guys did in school. Yes, for standard arithmetic. Yeah, exactly. Because when I was studying via Russian, it was dot. When I was in Ireland, I studied X. That was the first kind of introduction to it. All right, let's start with a bit of dot product. What do I need to know? I need to know anything? No. Okay, so the rule with dot products is very, very simple. Let's say I have a vector with 3 dimensions. We're doing 3 dimensions now. We're big boys and girls. We're moving on to 3 dimensions. And let's say I have a vector A. By the way, if I have a little arrow on top of it, it means it's a vector. And I say it has a position of 2i minus 4j plus 2k. I, J, K. Okay. Ooh, we got new hype train emotes. Thank you so much for the hype train. Really appreciate that. Sman, Spooky, Bog, Apple, and 2. I really appreciate the support. Thank you, lads. You're good eggs, as Cake Jumper would say. Then we have another vector, and we'll say that it's 3i plus j minus 4. Okay, so this are 2 vectors. You could plot them if you want very carefully, that's fine. That was my question. K in the first one. Oh yeah, I'm using hats. Sorry. Well, to be honest, I should be using the arrows. I've been using the arrows. I don't know why I switched to the hat. Apologies. I'll stick to using the arrow above them. My bad, my bad. Getting confused between my own stuff there. Hello, hello, welcome in, welcome in. Choo choo. Make them all hats. Wait, do you want me to make them all hats? Sorry. Okay, so if we wanted to do a dot product, so we wanted to multiply out these vectors, we can do something, called a dot product, but the outcome of it is a scalar. So what we can do is, we can do 2 things. We can grab these vectors and get a multiplication out of them. Usually you'll have to do that. For example, let me think about something. Electromag. Force is equal to Q times B or something. What's that one again? I'm trying to remember some electromag. But basically, you have 2 vectors, okay? There are situations where you have 2 vectors and you need to multiply them. But what's important to point out is that, well, is our answer going to be a vector or a scalar? Which one's it going to be? And it just depends on what it actually is and what we're expressing and what we're calculating. So the dot product, what's going to happen is that we're going to get a scalar answer. Me for burping. It means we're just going to get a number with no direction. So what's a scalar? So the difference between a scalar and a vector, a scalar is just something that has magnitude. So for example, speed is a scalar. That is me traveling at 40 kilometers per hour in my car. But if I said I'm traveling 40 kilometers per hour in my car in the direction northwest at 20-degree angle, that would mean that I have a vector. Like temperature. Temperature is a scalar, exactly. Temperature is a scalar. It doesn't have a direction associated with it. Okay, so if we... My 3D printer was making sounds, I wanted to make sure it wasn't broken. Exactly, 42 is a scalar, it's not a magnitude. I don't know, 69 might be a vector. I think 60... There is a position, definitely. Okay, I'm just gonna stop. Right, here are the rules. Here are the rules. If we wanted to multiply these two vectors out, there's a couple of very straightforward rules we need to do. I just want to make sure I'm not bullshitting myself here. It is as simple as that, right? Yeah, it is. Okay. What we need to do is we need to grab the I components and multiply them together. We need to grab the J components and multiply them together. And we need to grab the K components and multiply them together. And then add them all together. Then we get the answer out. So, let's have a quick look here. That's 2. So let's say A dot B. 2 multiplied by 3. That's the I component. Plus minus 4. What's the number in front of the J? J doesn't have a number, chat. What are we going to do? One, exactly. It's 1. There's no number in front of it. It means it's a 1. Plus 2 times minus 4. Don't forget those minuses. Those minuses are important. Time to give up. So let's multiply these guys out. 2 by 3 is 6. Minus 4 times 1. Minus 4. 2 times minus 4 is minus 8. In your heads or in your calculators, 6 minus 4 minus 8, that is minus 6. And here we go, we get the scalar answer of magnitude value of minus 6. So if we were given two vectors, it could be an electromagnetic field, it could be electric field, it could be a magnetic field, it could be a force. Sometimes we're just given a value and we have to do a dot product between them. This is how we do it. So note, we don't have a direction associated with this. We just have a number. So the general expression for a dot product is, if we want to do a general thing, would be to grab the component A1 and multiply it by B1 plus A2 multiplied by B2 plus A3 multiplied by B. What if we had 3 vectors and we needed to multiply all 3 of them? Well, let's say the third one was 1i. That would be 2 multiplied by 3 multiplied by 1. Minus 4 multiplied by 1 multiplied by 2, let's say. And so on and so forth. What's a 3 vector? It's the Irish word for 3. There we go. We're learning Irish today. So this would be the general expression of how to perform a dot product. The dot product is very easy. It's just multiplication. It's not too crazy. Cross product is where shit goes crazy. So we're going to learn a bit about matrices, a bit about, yeah. You're going to love me for this. What time is it now? I might have to do a strategic pee break. I'll leave this up on the board for a second. If anyone wants to pause the stream to take this down, I'm going to take it down because it takes a while to dry. Freeze the camera if you need to. Catch the piss bucket. It's okay. We're not in the mines today, so it's fine. Here we go. We'll be right back. We'll continue stream in a minute. I'm going to run ads. We're going to pee. Grab a cup of tea. Yeah, I'll make a cup of tea actually. I'll be back in a bit, lads. I'm going to start moving towards the other side of the circuit. Over time, there's not going to be any electrons left. And so you have a positive net voltage buildup here, a positive negative buildup of electrons here, and you have a big voltage difference across these two plates. So initially, when you first click the switch, there's loads of current going through. But as time goes, more and more and more of the electrons are built up on the other side, and you're basically losing current. You don't have as much electrons to work with, and as time progresses, you have less and less current. So that's the basic principle of how a capacitor works. Now, let's look at the classical design of a passive filter. This is your voltage in, your voltage out, a capacitor and a resistor. and then you flip it across here. So one of these is a high pass filter and the other one is a low pass filter. We'll figure out which one it is. So let's think about it. We have a current coming in, and AC current is a wave, right? Whee! And it's coming into our setup here. Think again how a capacitor works in a DC circuit. If you give it enough time to charge, basically the current is going to get less and less and less. However, in an AC circuit, you're constantly changing polarity, positive and negative, positive and negative. And what if I was changing polarity super quick? What if this time was very, very small? What would the current be? Because we're alternating the current so quickly, we don't give it enough time to charge and discharge the capacitor fully. The capacitor is saying yay, because it doesn't get enough time to charge. It allows loads of current to go through. It passes through freely and easily. It's very, very happy. So this is what we call a high pass filter with a capacitor. But another interesting thing that we can do is that we can switch the resistor and the capacitor. The reason there's a resistor in there is because there is this whole filtering process and what frequency you're going to be operating in. I highly recommend, again, checking out the organic chemistry tutor video that I've linked in this video, because there's no need for me to repeat the same thing. I would say exactly the same things as he does. Now, when we flip the resistor and the capacitor here, we have a wave coming in, as always, in the V in, and it could be a really high frequency wave or a really low frequency wave, we don't know. Dun 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 dun. And there's two paths it can take. Well, because a capacitor loves current that has high frequency, right? It wants to allow that current to pass through. Something that we say in this field is that it has low impedance. It has such low resistance that that type of current would rather take this path. And there's a ground usually in the system and it gets filtered out. So the high current coming in, the high voltage, the high frequency waves coming in will be passed around in this direction and to ground. They get filtered out, which allows the low frequency, the slow waves like this, where we give them loads of time to charge and discharge, which means low current. We allow them to pass through easily, and we call this then a low pass filter. Just to reiterate before, the high pass filter allows the high frequency waves to come in, but if you have a low frequency coming in, it blocks it. Because no current is going to get through. If you're giving it too much time to charge and discharge, if you increase this T more and more and more, it's just not going to pass a whole lot of things through. Now, the same principle can be applied to an inductor. Let me show you. Now, if you invest a lot of time in studying this, my recommendation is study one thing, like high pass filter with the capacitor, and study it thoroughly. All the equations, like I said, for the organic chemistry tutor, from my videos, from other people, and just study that super well. Understand the physics, understand the equations, understand the theory, and if you learn that one really well, not only will you know how to do all the other passive filters with inductors and capacitors, but you'll understand notch and noise cancelling and all of those other filters that exist for passive filters. If you know one extremely well, you know them all, because they're just opposites or inverses of each other, which is very similar to what an inductor is. So earlier I said a capacitor is two plates, there's electrons on either side, you extract all the electrons from one side, put them all in the other, build up of electrons here, not a whole lot of build-up of electrons here, the opposite, and you build up a big voltage. Let's talk about some... Hello, sorry, grab myself a cup of tea. Hi Curly, welcome in. Hope you're keeping well. Sorry I couldn't hang out too long on your stream last night. Your streams are very late on the weekdays, but the weekends I have no excuse. I don't. Hope you're keeping well. Good poop? Did not poop today yet. Did I poop today? Very weird question, but no. No, not yet. Soon, I'm sure. Morning, hi Chaotic, hi Young, welcome in. I hope you guys are keeping well. In this house, we obey the laws of thermodynamics. Do we though? There is still a lot of time left, that is true. May the poop forever be in your favor. True. We should do the physics of poop someday. That sounds TOS actually. You know what, never mind. I'll take it all back. Alright. Remind me to edit this part when I upload this on YouTube. Right, the next part is we are going to take those vectors that we're dealing with and we're going to do something called a cross product. And it looks a little bit horrifying. The idea behind a cross product, I actually have no reference for this, so let me pull up something. Okay, I'll wing it. It'll be fine. If you guys see a mistake, let me know. Let's say, let's do the same thing that I took it down actually, never mind. I was going to use the same vectors, but we'll write new vectors. So let's say A is equal to 2i plus 3j minus k. B is equal to 4i minus 2j plus 9k. Okay, so we have two vectors again. And then, whatever way, one is a force, one is a field, and they're both vectors, and you have to get a vector outcome out of them, you have to do something called a cross product. An angry product, exactly. So what we need to do here is we need to do some weird maths. Now, exactly, vector product, parallel piped volume. That's exactly what it is. That's usually what I think of when I think about this. Anyways, or is it the triple product more than anything? I think it's the triple product. Anyways, we're ranting a little bit here. So to deal with this, we need to express it actually a bit like a matrix. So if I were to express this as a matrix, well, we have the coordinates I, j, and k. We just lob in the numbers associated with them. So the A1 is 2, 3, minus 1. Remember, if k is on its own, it's just a 1. The number for B is 4, minus 2, 9. Voila! This is it expressed in a matrix form. I hope you guys see it. I know there's a lot of light reflection going on. Maybe... Is this better? This off. This light on. Is that a bit better to see the board this way? It might actually be better this way. Let me know. It's much better. Okay, perfect. We'll stick it with this then. Okay, so this is messy. How do we deal with this? Well, the cross product rule is interesting. Actually depends on how you were taught. There's two ways of doing it. I'll do it my way and then I'll show you the other way. It's not too different. But the way I try to see this is I think of two waves and the position of two waves. And they have an ijk coordinate and an ijk coordinate in which direction they're moving. And you're cross-producting them, trying to find the product between those 2 points. And so the I part is dependent on the j and k, the j part is dependent on the I and k, and the k part is dependent on the I and j. So that's kind of what we're doing here. When we grab one of these components, we're actually going to do the maths of the other two. I know it's a bit weird, but let's do the first part, the I component. The I component is going to actually be a 2x2 matrix of the j and k. It'll actually be 3, minus 1, minus 2, 9. That's the first part. I'm going to do it my way. The next part is going to be minus. There's a reason why. Just stick with it for now. Now we're going to look at the j component. We're going to look at the other two, the I and the k. That's a 2, minus 1, 4, 9, j. Minus sign there. And I just ran out of space here. Plus, the last guy, the k component, with these guys here. 2, 3, 4, minus 2. This is how we can express it. This is how we can do it mathematically. Some teachers will not do this with a minus sign, they'll do it with a plus sign. If that's the case, what will actually happen is they'll change this to a plus and they'll switch the order of these cells. It'll actually be minus 1, 2, 9, 4. Order will be opposite. Just an FYI, in case you were thinking back, I don't remember a minus sign there. It'll be the same thing. It'll turn out the exact same way. Looking at my 3D print. Not as spherical as I'd want it, but I learned it this way. So to each their own, and it's fine. That's completely okay if you learned it a different way. So, what do we actually do with these numbers? Well, it's in the name. We're going to cross multiply them. So, the first component here, let's start this maths. Maybe the red isn't very visible. Let me color. We're going to look at this first one. So, it's going to be 3 by 9 minus 1 minus 2. That's the first I component. Remember the minus sign? There's a minus sign in our case. We're going to cross multiply. That's 2 by 9 minus 1 times 4. And finally, the last plus sign here, that's going to be 2 times minus 2 minus 3 times 4. Now, I did add something weird in these equations. I drew a whole bunch of lines. Oh, shit. I stepped over my own slippers. Not new slippers, actually. What do those lines mean? This line here and this line here. Does anyone remember what lines like that actually mean when we deal with maths? Magnitudes? Absolute values, exactly. We're trying to get the absolute value. So the idea behind it is we could do some maths in here and we could end up having a minus number in there. It could be -3. But because we put the absolute bars between them, it means that we're going to, no matter what it is, we're going to make it a positive value. So that's what those mean.
That still only counts as one.
So, unfortunately I'm running out of space. So what we're going to do is we're going to hop between two boards. So 3 times 9 is...
That still only counts as one.
27. Yeah, it is 27. I was questioning myself. 27. -1 times -2 is +2. Another minus, -2. Okay. 2 times 9 is 18. -1 times 4 is -4 with another minus sign plus 4. Two times -2 is -4. 3 times 4 is 12 with a minus sign, -12. With a K. And that is the expression that we get here. Let's continue with the maths. 27 minus 2 is 25. 18 plus 4 is 22. And -4 minus 12 is -16. But because it's a magnitude, it's +16. So the cross product between those two vectors, between these two guys, this. So as you can see, when we did the cross product, we got a vector. When we did the dot product, we did a scalar. Sorry, I just saw the absolute cinema. That's good. That's a good joke. You should post that, Science Bish. That's an actually good, crafty, witty joke. You outdid yourself, Science Bish. You outdid yourself. wants to check my maths, please go ahead. If I made an arithmetic mistake somewhere. So, that is, yep, that's maths. That is cross product. Now, the last thing I was thinking about doing, and we have no problem doing it, is something called a triple product. What if we were an absolute piece of, you know, whatever, and I said, well, hold your freaking horses. What if I told you do this? Dun, 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 dun. Because if we were just doing normal multiplication, and I told you 2 times 4 is equal to 8, right? But then I got 3 numbers and I said 2 times 4 times 2, that would be 16, right? I hope it's 16. That's kind of straightforward and simple for us in our human brains to do just normal multiplication. But what if we had a dot product and a cross product of a vector? We had both of these things. And again, we have actually expressions like this in Electromag quite classically. We have a dot product and a cross product put together. How do we solve it? Well, basically it's a 3x3 vector, which is really, really interesting. Please do elaborate more on the difference between the nomenclature for hats and arrows. I think hats is with the Hamiltonian. In this case, it doesn't matter. If you guys want to go into the story and delve the difference between them, I'm just using hats because I'm used to it. It's something that we tend to do in physics. There is technically, if I remember, a story with the whole expression of the Hamiltonian, if that's the branch that we're going into, but it's not something that that is too important at the moment. So, to get the cross dot product between them, it's basically a matrix of all 3. We usually express it that way anyway. But how we solve it is very interesting as well. So I'll show you this now. So let's say we had AB. Okay, let's do another one, because I can't keep switching the board. So let's say we had A is equal to 2I plus 3J minus K. B was equal to I plus 6J minus 2K. And C was equal to 3I minus J plus 4K. So these are our 3 vectors. How would we express it? Well, this guy can be expressed as following. We list them like a matrix, like we did before. That'll be 2, 3, minus 1. 1, 6, minus 2, 3, minus 1, 4. But the way we're going to do it is you cross product each parameter. Remember how we did the cross product? We're basically going to do this to B and C, and we're going to multiply it by A1. We're going to grab this guy of B1, C1, B3, C3, we're going to do the same thing and multiply it by A2, and so on and so forth. We're basically combining those 2 things together. So how would we do that mathematically? Well, running out of space. I need a bigger board. We're going to need a bigger board. Hi, Ayad. Welcome in. Let's do the maths out for these guys. So what we're going to do is we're going to cross product these guys first, the B and C. Let's do that. That's 6 by 4. 6 by 4 minus 2 minus 1. Okay, times the dot product. We did do the product, which is a value here, 2. Multiply by 2. So whatever we get here, we're going to multiply it all by 2. That's going to be the first step. Next part. Happy holidays. Hi, Elise. Welcome in. We mathing hard. Scalar triple product. So now we're going to look at this guy. It's going to be 1 times 4. 1 times 4 minus 2 times 3 times a2, and a2 is equal to 3. Finally, last but not least, we're doing 1 times minus 1 times 3 times 6 dot product of last one left minus 1. And here we go. Let's slowly do the maths out. 6 times 4 is 24. Minus 2 minus 1 is 2 with a minus 2. 1 times 4 is 4. Minus 2 times 3 is minus 6 with another minus plus 6. And we have 1 times minus 1, which is minus 1. 3 times 6 is 18 with a minus 18. All times minus 1. All right, let's do the maths out. 24 minus 2 is 22. 22 times 2 is 44. 4 plus 6 is 10. 10 times 3 is 30 with a minus 30. Minus 1 minus 18 is minus 19 times that's just 19 because it's a magnitude. 19 times minus 1 is minus 19. So 44 minus 30 is equal to 14. 14 minus 19 is minus 5. Can anyone check my maths? This is where things can absolutely go downhill any moment. Let me know if I did anything wrong, but that is how you get the scalar value of a triple product. It's basically a scalar value. So even though there's a cross product in there, you might say, oh, should we not get a vector answer? But if you're scaling anything, if you're doing anything with scaling it, i.e. getting a magnitude, you can't extract a vector out of it. So you will get a scalar outcome. So you're absolutely right that this could also be referred to as the scalar triple product expression, Grim. We're absolutely on the money on that. And that finishes our introduction to vector analysis. Obviously, there's a lot more application we could do, like where do we actually use this? Mostly when I teach this, I do like volumetric expressions, like shapes and sizes and how shapes change and stuff like that. So the next step, so all this is, Grim, is mathematics. All I'm teaching you is a mathematical skill to deal with two vectors, and then if you're in your equation, you're multiplying them. How do you do it mathematically? The next step, I think, is a little bit better, in my opinion, is when we do differentiation of
That
vectors.
still only counts as 1.
So that actually is where things go, well, for me anyway. So vector differentiation would be the next step. So if you guys are willing to wait until the new year, I think that's a lesson that we could do, vector differentiation.